Hi, so today we'll look at Q and K and what's the difference between the two of them. So K, being the constant, the equilibrium constant, tells us the concentration or pressure at equilibrium. In contrast to that, Q tells us the concentration or pressure at any given time. So how do we write Q? How do we write the formula for that? Well, it is similar to that of K. So that means it would be concentration of or pressure of products divided by that of reactants. Using the above equation, we can write it as just like this. And don't forget the powers. But if you notice, it looks literally similar to that to how we write K. So to create a difference over here, we can just add in T at the bottom to say that, oh, it's at any given time. Although when you really write it using numbers, you don't really need to mention the T, but to create a difference in the formula, we can just write T over here. So now we'll compare QC with KC and see what does it tell us about our reaction. So for starters, we need to remember that every reaction wants to achieve equilibrium, and Kc refers to the equilibrium position. So with the first one, we have Kc greater than Qc. That means that the point we are at currently, we haven't yet reached equilibrium. We want to reach equilibrium. So that would mean that our forward reaction is being preferred. So that would also mean that whenever you're given with a value for Q which is lower than the value for K, that would mean that your reaction is moving forward. There's another way to know that. So let's say that my Kc value is 4 and my Qc value is 2, because Qc is less than Kc for the first one. That would mean that I need to make my Qc value greater enough to reach Kc. So I need to make that 2 equal to 4. How can I do that? Now there are two ways I can reach that conclusion. So either I can increase the amount of my products, so that would mean more products are being created, or I can decrease the amount of reactants, because you know it's in a fraction, so lower denominator would get you a bigger answer, or bigger numerator would get you a bigger answer. So because I want a bigger answer, I can increase the amount of my products or decrease the amount of my reactants. And both of those ideas refer to your reaction moving forward. More products being created and more reactants being consumed. Now for the second one, where my Qc is greater than my Kc, that would mean that my backward reaction is being preferred. Now using the same ideology, let's say my Kc is 2 here, my Qc is 4. Now this means that my reaction has gone ahead of equilibrium. So now I want to bring my reaction back to the point of equilibrium, because my reaction is ahead of equilibrium now. To bring it back, I will say that my backward reaction is being preferred. And there's another way we can look at it is as because I want my Qc value to lower, I want the 4 to reach the value for Kc, which is 2. How can I do that? Yet again, there are two ways to do that. Either I can decrease the amount of my products or increase the amount of my reactants. So increasing amount of reactants, decreasing amount of products, both refer to the fact that your backward reaction is being preferred. And the third one is where both of them are equal. So your 2 equals 2, 4 equals 4. That would mean that at this point, you have reached equilibrium. You are at the right point. Your reactions they've achieved equilibrium. So a trick of remembering all of this would be to think of all of it as a timeline. So this is what my friend actually taught me. So let's say I have a timeline right here, and in the middle I have my Kc, which is something that I want to achieve, and then Qc is here, Qc is here, because Qc is like concentration at any given time, so it could be time that is before reaching the equilibrium or after the equilibrium. So if my Qc is less than my Kc at this point, right, that would mean, because I want to reach equilibrium, so my Qc is gonna go ahead, because Kc is ahead right now. So that means that my forward reaction is being preferred. And then let's say my QC is greater than my KC over here, because QC is lying far ahead of KC. So now on my timeline, I can notice that I want to move back to reach KC. So this refers to the fact that I have a backward reaction. And at this point, my QC equals my... Now we'll go ahead and look at this question. So I'm provided with my KC, which is 0.11, and I need to find the equilibrium concentration of ICl. So I'll notice how my equation is already balanced, so I'll just write my KC, which is products divided by reactants, concentration of them, ICl, and don't forget the square because 2 moles of ICl are available. Now I need an ice table here. The reason I need an ice table here is because I don't have the equilibrium concentrations. I do have KC, but I need to find the equilibrium concentration. That can only be done using an ice table. Now the information I'm provided with is moles and liters. I'm not provided with the molar concentration. So in order to find that, I can use the formula, this, and then solve it for concentration, which would be number of moles divided by volume. Now if I read through the data I'm provided with, it says that 0.7 mole of I2 and 0.7 mole of chlorine are initially mixed in a 2-liter flask. So that means that I have Cl2 and I2. So this would be 0.75 divided by 2, which gives me 0.75 molar, and same goes for I2 over here using this formula. And then because initially I have I2 and Cl2 present, then ICl would be 0 because it's the start of the reaction and I don't have any of my ICl present. Now I do understand that ICl is a reactant, so I have 0 reactants, but I have products over here. So basically my reaction is moving backwards. But well, there are 2 ways to solve it. So let's say I keep my equation the way it is. So let's say my ICl is in the reactant side, and then I2 and Cl2 are on the product side. That's how I solved it. That's how I made the KC equation, and then that's how I also I'm gonna fill up the ice table. So when I talk about change for ICl, it's gonna be positive 2x. The reason why there's a 2 is because I have 2 moles of ICl, and then the reason why it's positive, it's because it's getting made, so it's increasing in concentration. And then for ICl and I2, it would be negative x because they're getting used up and they just have 1 mole available. And then at my equilibrium, I'll just add them up, which would be 2x, and then 0.375 minus x, 0.375 minus x. Now I can use this and put in my values. This would be 0.375 minus x. Now I can put a whole square on this because the concentration at equilibrium for Cl2 and I2 are the same, so I can just put a whole square, and there's a whole square here. Now I can take under root here, cancel this out. So my x would equal 0.2254. But because I'm asked the concentration for ICl, if I notice my ICl is 2x, so I need to multiply. In order to get the concentration for ICl, I need to multiply it with the value for x with 2, which would get me a 0.45 molar. But let's say I do it the other way. Let's say rather than getting confused with, because usually reactants are getting used up, products are being made, so one might make mistakes at this point with the positives and the negatives. So let's say, to make it easy on me, I shift my equation. Because the reaction is going backwards, so let's say I make my products my reactants and my reactants my products. So ICl is here is my product, and Cl2 and I2 are my reactants. The reason I did it is because I know initially I don't have any of my ICl available, although initially I do have I2 and Cl2 available. So it makes sense for reactants to be available initially. So let's say I shift the equation. So over here I'll try filling it up now. So initially 0.375 molar, 0.375 molar available, and ICl, obviously it's a product now, so it's 0, similar to how we did it for this ice table. And change would be negative x, and for ICl would be positive 2x, similar to how we did it before. And at equilibrium we just put them all together. But now here's the trick, here's the main point, not even the trick. So because Kc was given to be 0.11, but that was because I was following this equation that's given right here, which is going forward. But because I flipped my equation, when I write Kc here, it would be different, because Kc is reactants divided by products. So for this one, I have my product as ICl squared divided by Cl2 I2. And if you compare this Kc with this Kc, you'll notice that I basically took the reciprocal, I flipped them. Because of that, my 0.11 is not 0.11 anymore, because I also need to take the reciprocal for that value. So Kc now, the new Kc I have is 1 divided by 0.11. And ICl would be 2x squared, and then 0.375 minus x. I can just take a whole square because I2 and Cl2 have the same concentration. And now I'll take the under root, similar to how I did earlier, cancel it out, and my x would be 0.2254. The value for the change is the same, the x remains the same. And then ICl concentration would be 2 times of x, which would again be 0.45 molars. Now we'll look at part B of the question. So over here, when it says the reaction will proceed towards products or reactants, or does it stay the same, that insinuates that they want me to they want us to perform the Q test. So that means I need to compare my QC value with my KC value. So I already have my KC value from above, which is 0.11. I'll write down the QC equation, which would be similar to this one, the equation provided here. Well, the equation we wrote ourselves, the formula we wrote ourselves, it would be same as this. However, while I'm gonna plug the values in, I notice that I don't really have the concentrations. The information I'm provided with gives me the moles. I need to find the concentration, so I'll use this formula again to find the concentration. However, I need volume, so it's safe to assume that my volume, because the flask is 2-liter flask, it's safe to assume that the volume is 2 liters. But because it's 2 liter for all these 3 reagents, so because the volume is the same, I don't really need to plug in this formula. I can just straight up use the number of moles that I'm provided with. If you want to, you can find concentrations, but because the volume is the same, so it kind of cancels out. So you can just, your answer for concentration is going to be the answer you have for your moles. So that means my concentration of Cl2 is 1.8, which is similar to the moles of Cl2 I've been provided with, and I2 would be 1.5. ICl would be 3, and then whole squared. So you could either write 1.8 divided by 2, and then 1.5 divided by 2, and then 3 divided by 2 whole squared. But the answer you're gonna get for this is gonna be equal to the answer you're gonna get for this, because 2 is the common denominator in all of these 3. So to make it easy for us, we just write it easily, and this is gonna get us the answer 0.3. Now, because 0.3 is the answer for QC, which is greater than KC, so if I draw my timeline here, my KC in between, my QC is here and QC is here. Now QC is greater than than KC, so my reaction is gonna move backwards, because I have a higher value for QC. It wants to achieve equilibrium, so it's gonna move backwards to a lower value, because KC is at a lower value. So my reaction, actually, I would say that my reaction moves backwards. backward reaction preferred, and that's it. So I'm gonna get more of my reactants over here. So that means that in this equation I'm gonna have more of ICl being produced rather than I2 or Cl2. So I'm gonna have more of my ICl because my backwards reaction is being preferred and my my reactants are being formed. Now we'll look at another question based on equilibrium. The equation I've been provided with is already balanced, so I can just straight up write a Kc for this, which would be AHI. So it's products divided by reactants. So concentration or pressure of them. So here I'm dealing with concentrations. Now I'll need to make an ice table because it asked me to how many moles of HI present at equilibrium. So to find the equilibrium concentrations in the moles, I need to make an ice table. Now over here I'll notice how I am provided with volume and moles, not the concentration. So I'll use the formula to find concentration, which would be for H2 it would be 2 divided by 0.5, which would equal 4 moles, and then divided by 0.5 would equal 2 molar. And then HI is my product, we're making it, so initially I would have a 0 of it. Change would be negative x, and this would be positive 2x because products are being made and reactants are being consumed, and then that's how positive negative comes about. And then 2 is over here is 2 because of the 2 HI moles I have available. For at equilibrium I would have 4 minus x, 2 minus x, and then 2x. Now I have my K value here. So something about the K value here is that the K value is 50, which is quite big. So usually the K values we have are something 10 times 10 raised to the power negative 5 or lower than that. So if it's negative 5 or lower than that, we can use small x approximation. But over here, because the K value is quite big, we can't really do that. And then a really big K value also refers to the fact that my reaction is moving forward, like it's the forward reaction is being preferred. So this is actually squared. Now this would be 50 equals, I'll need to you'll solve this and then you actually get 400 minus 300x plus 46x squared equals 0. So because it's a quadratic equation, I need to use the quadratic formula here. So I'll say that x equals negative 300 plus minus under root negative 300 squared minus 4 times 46 times 400 divided by 2 times 46, 2a. So yeah, so my x values would be 4.65 and then 1.86. So because both of those values are positive, the dilemma here is that which one to use. So how you select the x value is based on the equilibrium concentrations here. So let's say that let's say I pick the first one. If I subtract 4 minus 4.65, I'm gonna get a negative answer. I can't have a negative answer for concentration, so 4.65 is obviously not going to be your choice. It's going to be 1.86. So the question was how many moles of HI present. So HI is 2x, so x is 1.86 now, so I'll have to multiply 1.86 with 2 to get my answer, which is 3.8 moles for HI concentration. But because this is concentration, it asked me to find number of moles. I can use this formula here, and number of moles equals 3.8 times 0.5. This would give me 1.9 moles. Now we'll look at part B of this question. because it says over here whether my products are being formed or my reactants are being preferred, that means that they want us to perform the Q test. So we'll write down the equation for that, which would be similar to the one we wrote above. H2, I2. Now we had our Kc value as 50. Now I need to find the Qc value from here. So I'll plug in my values, but notice how I don't have concentrations over here. I have moles and volume. So I have my formula, which is number of moles equal concentrations times volume. So concentration and number of moles by volume. But I don't really need to really use it because my volume here is the same for all of these three reagents. So it is the common denominator. So if you want to, you can still find concentration, but because volume is the same, you can just straight up use the mole values you have, and it's still going to give you the same answer. So n cubed divided by H2, which is 3, not n2, but like 9 squared, 50. This would give me a value of 1.8. Now 1.8 is relatively greatly smaller than Kc. That means if I draw a timeline, Kc is in the mid, Qc are on both sides because Qc is like a concentration at any given time. So my Kc is far behind my Qc right now. It is 1.8. So in order to, because every reaction wants to reach equilibrium, in order to reach equilibrium, my reaction needs to move towards Kc, so it's moving forward. So I can say that forward reaction is preferred. And that's it.